Hello and welcome to yet another video of Cornerstones of Math. Today I am going to address one of the most famous properties in the study of series, that the sum of the reciprocals of all prime numbers, which is this series right here, diverges. In this video I am going to prove it. Now there are many ways to prove that this series diverges, and you can easily access them. For example, you can go check this Wikipedia article anytime you want. The method that I'm going to show you in this video may share same principles with some of the method in this article, but not 100% the same way. This video is just demonstrating one of the many methods, and without further ado, let's jump right into it. In this video, let us denote the sequence of prime numbers as Pm. Then we want to prove that this series of 1 over Pm diverges. We are going to use the good old proof by contradiction method. That is, we assume that this series converges, and we are going to show that contradiction occurs under that assumption. So as a starter, let us assume that this series converges. We are going to derive a contradiction by setting up some inequalities. The first inequality comes from the following observation. Since we just assume that this series converges to some finite value, we can simply cut out some of the front terms so that the sum of the remaining terms become less than 1/2. In a more formal language, we can say that there exists a natural number capital N such that the sum of 1 over Pm, where m changes from n plus 1 to infinity, so this series, starting from 1 over p n plus 1, is less than 1/2. As for the number on the right hand side, you can also use other values such as 1/3, 1/4, etc. But let's just use the simplest number, 1/2. So we have this inequality. The next step is that we raise each terms to nth power, now with lowercase n, which denotes an arbitrary natural number. Then on the right hand side we have 1/2 raised to the nth power, which is greater than this entire series raised to the nth power. This seems a weird thing to do, but it becomes even weirder. Since n can have any natural number values, we can just substitute n with 1, 2, 3 and so on, and add them up. This leads to this inequality, where now both sides are infinite series with infinitely many values for n. And this is our first inequality. Needless to say, the left-hand side became rather complicated. So why am I doing this? Well, the first thing to notice here is that now we have a familiar series on the right-hand side of the inequality, the geometric series. And we can at least handle geometric series easily, right? And the reason why I did this becomes even clearer after I explain the second inequality. But before we get to the second inequality, we have to introduce some new numbers. In order to do that, let us go back to this step where we have defined the natural number capital N. Capital N is defined in a way that if we add up the reciprocals of primes starting from 1 over p of n plus 1, then the entire sum becomes smaller than 1/2. Now, let us introduce the number q, which is defined as the product of all primes from p1 to pn. That is, q is equal to p1, p2, p3 times so on, all the way up to p capital N. Then, for any natural number small n, which we have already used in the previous step, we can think about the number 1 plus nq, which is equal to 1 plus n times p1 times p2 times so on times p capital N. Let me emphasize again in order to avoid confusion. Capital N is the specific number satisfying the specific condition, which has single value. Small n refers to arbitrary number, and we are going to consider the case where small n can have all of these values. Then we can claim the following. For any natural number small n, the prime factors of 1 plus nq, which is this number, consist only of the primes greater than or equal to p capital N plus 1. Let me briefly explain why this is true. The equivalent statement is that 1 plus nq is not divisible by any of prime numbers from p1 to p capital N. So if we deny this conclusion, then we can say that 1 plus nq is divisible by some prime number pk that falls into this interval from p1 to p capital N. Then we can say that 1 plus nq is equal to n prime times pk for some natural number n prime. That is 1 plus n p1 p2 times, and there has to be pk somewhere in the middle, and ... times p capital N is equal to n prime times pk. Notice that this term and this term are both multiples of pk, but their difference is 1, which is impossible. Therefore, we know that this statement is true, that all of the prime factors of 1 plus nq comes from prime numbers that are greater than or equal to p capital N plus 1. For example, we can think of number 1 plus n1q whose prime factorization is p capital N plus 1 times p capital N plus 2, 1 plus n2q whose prime factorization is p capital N plus 1, p capital N plus 2, p capital N plus 3 squared, and number 1 plus n3q whose prime factorization is p capital N plus 27 to the power of 30 times p capital N plus 42 to the power of 73, and so on. So now with this property established, let's get back to this weird looking series of series, where this being less than the series of powers of 1/2 was inequality 1. If we write the left-hand side in a longer form without this outer sigma, then we obtain this expression, where you can easily identify the terms corresponding to small n being 1, 2, 3, and so on. Here, let us write in even longer form without these inner sigmas as well. Then we have this expression. And let us ponder on this question. What if we expand all of these? What kind of terms can we find in the expanded version of this expression? Well, by keen observation, you can easily notice that the expansion of this series contains every possible product of 1 over p capital N plus 1, 1 over p capital N plus 2, 1 over p capital N plus 3, and so on. For example, it contained terms like 1 over p capital N plus 2 squared, 1 over p capital N plus 1 times p capital N plus 2 squared, and even this weird thing such as 1 over p capital N plus 3 cubed p capital N plus 100 to the power of 5 times p capital N plus 1000 to the power of 7, and on and on. Here, the first example comes from the expansion of the term with second power. The second example comes from the term with the third power. And as for the third example, since 3 plus 5 plus 7 is equal to 15, it comes from the term with 15th power. Moreover, we can draw additional conclusion. That is, this series contains every possible case of the reciprocal of 1 plus nq. This is true because we have shown that 1 plus nq only contains prime factors that are greater than or equal to p capital N plus 1. Therefore, we can say like this. This series contains all the reciprocals of the form 1 over 1 plus nq, hence 1 over 1 plus q plus 1 over 1 plus 2q plus 1 over 1 plus 3q and so on, plus some possible extra terms that do not fit into any of 1 over 1 plus nq. This is greater than or equal to this series at the front, which is the infinite series of 1 over 1 plus nq. And this is our second inequality. And with this second inequality obtained, the next step is obvious. From steps 1 and 2, we have obtained this series of inequalities. Here, the series on the rightmost side is the geometric series that clearly converges. As for the series on the leftmost side, you can easily notice that it has the same degree as 1 over n, hence it increases at approximately the same speed as the summation of 1 over n, which is a diverging series. Or if you want to be more rigorous, you can use some convergence test such as comparison test. Notice that 1 over 1 plus nq is greater than 1 over nq plus nq. So we have greater than the summation of 1 over 2q times 1 over n, which is a diverging series. Or we can even use the integral test, where the convergence of the series can be determined by the convergence of the improper integral of 1 over 1 plus xq from 1 to infinity. If we do the integral, we obtain this antiderivative, which diverges. In any way, we know that the series on the leftmost side diverges. Therefore, the middle part is wedged between two series, with diverging series on the left and converging series on the right. This is impossible, hence a contradiction. Therefore, our very first statement is true, which is that the sum of the reciprocals of prime numbers diverges. And that's all for today's video. Thank you for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.